Hello, my name is Tiago, and I'll present this work called the nonlinear structural probe. This was mainly led by Jennifer, but me, Naomi, and Ryan also helped. So I'll start with a quick overview of what probing is. Probes are mainly supervised models trained on top of fixed representations, like the contextual representations from BERT. And they allow us to explore how much these language models know about syntax, or how much knowledge is encoded in the representations. And the very simple pitch of this idea is that high accuracy means that knowledge can be extracted, and low accuracy means it can't. So one of the most famous probes out there is the structural probe, proposed by Hewitt and Manning in 2019. And this probe learns a metric function between two embeddings. So they use a linear transformation of each embedding, and they train this probe to approximate syntactic tree distances. And by doing this, they can analyze how much these syntactic distances are encoded in the representations themselves from BERT. The main novelty in our work is realizing this is a metric learning problem and that we can apply the kernel trick to it. So what is the kernel trick? It just says that we can replace a metric with a feature map phi by a positive semi-definite kernel. So you can see from this function, the left side of the function resembles the structural probe very well. And we can rewrite it in terms of kernels on the right side of this equation. So if we go back to this structural probe, it represents this feature map, which is basically a linear transformation of the contextual embedding. And we can rewrite it as the linear kernel, which is basically this dot product between the linear transformations of two embeddings. And you can see that if you apply this kernel back at the equation on top, you recover the left side of the equation and the structural probe perfectly. So what we do in this work is we replace the linear kernel with nonlinear ones. So we'll make use of polynomial kernel, the RBF kernel, and the sigmoid kernel. And we'll mostly focus here on the RBF kernel, which is also called the Gaussian kernel. But the other two are interesting in terms of serving as baselines for our analysis. So let's discuss why to use kernels in the first place. There's a long discussion on simple versus complex probes, what exactly they tell us about encoded knowledge, what is just learned by the probes themselves, what is actually being represented by the representations themselves, the fact that we can train if our probes are too complex, we can train them on top of random embeddings and get good results. So the simplicity versus complexity stops us from analyzing the structure of the encoded knowledge in a controlled manner. So this is where the nonlinear versus linear structural probes come in. And both these probes have exactly the same number of parameters. And by introducing the nonlinear kernels, we only change the kind of the shape of the function that they can learn, but without changing their capacity or the number of parameters that they can use. So it controls for probe complexity up to some point. Like you can argue that this non-linearity introduces complexity, but we'll assume that number of parameters controls for probe complexity perfectly in our analysis. So let's dive into our results. Do these non-linearities help? And in this presentation, we'll mostly focus on the UUAS results, but you can see a longer discussion on the Spearman correlation in the paper. So in terms of UUAS, the RBF nonlinearity improves over the linear kernel in all the analyzed languages. But this is not the case for the other nonlinearities. They are not consistently better or worse. What this tells us is that it's not only the nonlinearity that is allowing these RBF kernel probes to do better than the linear ones, but it should be something about the shape of the function that they represent themselves. So we can dive in more on what the RBF kernel is. And before that, let's recap what BERT's attention is. So BERT learns an attention function between two embeddings. And this attention is represented by the dot product between a query and a key vector divided by the square root of the dimensionality of these embeddings. And the exponential function here represents the softmax that is run on top of this dot product. The RBF kernel is represented by this top-bottom function there. But we can expand this square distance, and we find this second equation here, which is, again, a dot product between linear transformations. And if we look at both of these equations side by side, we find that they are remarkably similar. And what this suggests, together with our previous results, is that BERT likely encodes syntax in an RBF-based space. So as our conclusions for this work, we say that people shouldn't go linear by default. They should think about the model when designing their probes. How should that specific model encode that specific information? And that BERT likely encodes syntax in an RBF-shaped space. And that's it for this presentation. Thank you, and we'll see you in the question answering session. Let me stop recording here.